That little black and white square you just scanned at the restaurant, or on a billboard, or on a vaccine certificate, or on a product you ordered online. That square is one of the most quietly revolutionary inventions of the last 30 years. But here's what I want to ask you today. Have you ever stopped to wonder? Could we ever actually run out of QR codes? Like, there are billions of them, printed on billions of products, used by billions of people every single day. Surely at some point that we use them all up, right? No. And the reason why is going to completely change how you think about information itself. What even is a QR code? Before we get into the numbers, and trust me, the numbers are absolutely insane, let's make sure we're on the same page about what a QR code actually is. QR stands for Quick Response. It was invented in 1994 by a Japanese engineer named Masahiro Hara, working at a company called Denso Wave. His original goal? Tracking car parts on an assembly line. Barcodes weren't cutting it anymore, like they could only hold about 20 characters. He needed something that could carry more data, faster, so he designed a 2D matrix, a grid of black and white squares, that could encode information both horizontally and vertically. This was the key insight. A traditional barcode is essentially a one-dimensional strip of data. A QR code is a two-dimensional grid. Instead of one line, you get a whole canvas. And on that canvas, there are a few key regions. The three large squares in the corners. Those are called finder patterns. They help your phone's camera locate and orient the code, no matter what angle you're holding it. The timing patterns. Those alternating black and white lines that run between the corner squares, helping the scanner figure out the grid's size. The alignment patterns. Smaller squares that help correct for distortion, like if the code is printed on a curved surface. The data modules. The actual information encoded in the remaining black and white squares. And the quiet zone. The white border around the outside that separates the code from everything else around it. Now here's where the magic starts. The data in a QR code isn't just raw binary, it's encoded using something called Reed-Solomon error correction. This means even if part of the code is damaged, dirty, or obscured, up to 30% of it, your phone can still read it perfectly. That's why you can put a logo right in the middle of a QR code and it still works. Pretty elegant. But we haven't even gotten to the numbers yet. The math behind the madness. Here's where things get wild. QR codes come in 40 different versions. Version 1 is a 21 by 21 grid, the smallest possible. Version 40 is a 177 by 177 grid, the largest standardized size. Each version is a little bit bigger, and each step up gives you dramatically more data capacity. Version 1. QR code can hold 41 numeric characters or 25 alphanumeric characters or 17 bytes of binary data. That's not a lot. Enough for a short phone number or a tiny URL, but a version 40 QR code? That thing can hold 7,089 numeric characters, 4,296 alphanumeric characters, 2,953 bytes of binary data now. Here's the number I want you to think about. Because QR codes are ultimately binary, like every module is either black or white, a 1 or a 0, the total number of possible unique QR codes is enormous. Let me put it this way. A version 1 QR code has 21 times 21 equals 441 modules, but subtract the fixed structural patterns, the finders, the timing strips, and you're left with somewhere around 152 data bits that can be freely varied. 2 to the power of 152. That's 5 septillion, 708 sextillion, 990, quintillion, 770 quadrillion, 823 trillion, 839 billion, 524 million, 233,000, 143,000, 877,000, 797,000, 980,000, 545,000, 530,000, 986,000, 496. I'll say that again, in a more useful way. That is approximately 5.7 times 10 to the power of 45. For context, the number of atoms in the observable universe is estimated to be around 10 to the power of 80. So we're not quite at more than atoms in the universe territory with just version 1. But version 40? Now we're talking about a 177 by 177 grid with over 31,000 data bits. 2 to the power of 31,329. I won't even try to say that number. But I'll tell you this. It has over 9,000 digits. The number of atoms in the universe only has 80. We will not run out of QR codes. Not in your lifetime. Not in the lifetime of our sun. Not in any time scale that has a name. How many QR codes are actually being used? Okay, but let's bring this back to Earth for a second. How many QR codes are actually out there right now? This is actually hard to measure precisely because anyone can generate a QR code. It's an open standard. Denso Wave still holds the patent, but they've deliberately chosen not to enforce it, meaning QR codes are essentially free for the whole world to use. What we do know, as of recent years, over 6 billion QR codes are scanned annually just in the United States alone. Globally, QR code usage surged over 400% during and after the COVID-19 pandemic, largely due to contactless menus, check-ins, and payment systems. China has taken QR codes to an extreme. Platforms like WeChat Pay and Alipay process hundreds of millions of QR-based payments every day. In many Chinese cities, you use QR codes to buy street food, ride a bike, enter a building, and even donate to a temple. Global QR code payment transactions are projected to exceed $3 trillion in the coming years. And yet, even with all of this usage, humanity has barely made a scratch in the available address space. Think about it like IP addresses, but almost incomprehensibly larger. The entire internet ran out of IPv4 addresses, 4.3 billion of them, within about 30 years. That seemed like a lot in 1983. Wasn't. QR codes? The number of possible unique codes dwarfs IPv4 like the ocean dwarfs a raindrop. The infrastructure of uniqueness. Now you might say, okay, but aren't most QR codes just URLs? Don't they all point to the same websites? Doesn't that create collisions? Great question. Let's talk about how QR codes actually work in practice. There are two main types of QR codes. Static QR codes. The data is literally encoded in the pattern itself. The URL or text is baked right into the image. Scan it 1,000,000 times, it always gives you the same answer. These are cheap and simple but can't be changed once printed. Dynamic QR codes. These encode a short redirect URL, usually pointing to a server that then redirects to wherever you actually want to go. The QR code itself never changes, but the destination can be updated at any time. This is how businesses track analytics, run seasonal campaigns, or fix a broken link without reprinting anything. Here's the clever part. With dynamic codes, you only need the QR code to encode a short, unique ID. Something like qr.example.com/x7kp2, and the server handles the rest. How many unique short codes can you make from even a 6-character alphanumeric string? 62 to the power of 6 equals 56 billion possible codes. And you can always go longer. So the ecosystem of QR codes isn't just theoretically infinite. It's been deliberately engineered to scale with demand, almost without limit. Error correction, the secret superpower. Let's talk about something that doesn't get nearly enough credit. Error correction. QR codes use a mathematical system called Reed-Solomon error correction, originally developed in 1960 by Irving Reed and Gustav Solomon, two mathematicians at MIT Lincoln Laboratory. The core idea: you add redundant data to a message so that even if part of the message is lost or corrupted, you can reconstruct the original. In QR codes, there are 4 error correction levels. Level name can recover if L. Low, up to 7% of data is damaged. M medium, up to 15% is damaged. Q quartile, up to 25% is damaged. H quartile, up to 25% is damaged. H high, up to 30% is damaged. Level H, high, means you can obliterate nearly a third of the entire QR code and it'll still scan. This is why you can put artwork, logos, and photos in the center of a QR code. Those pixels are used up by the image, but the Reed-Solomon system fills in the gaps. This error correction overhead actually reduces the maximum data you can store, but it means QR codes survive the real world. Scratch stickers, smudged ink, bad printing, curved surfaces, partial shadows, they handle all of it. And here's the subtle implication for our never running out thesis. Error correction doesn't reduce the number of unique QR codes. It just means each unique code takes up a bit more physical space in the grid. The combinatorial space is barely touched. What would it actually take to run out? Let's indulge a thought experiment. Imagine a future civilization so obsessed with QR codes that they decide to tag every single atom on Earth with a unique QR code. The Earth contains approximately 10 to the power of 50 atoms. A version 40 QR code supports 2 to the power of 31,329 unique values, a number with over 9,000 digits. Could we handle it? Not only could we handle every atom on Earth, we could handle every atom in the Milky Way galaxy, estimated at 10 to the power of 68 atoms, and still be infinitely far from exhausting the address space. We could tag every particle in the observable universe, every proton, neutron, electron in its estimated 10 to the 80 atoms. And version 40 QR codes would still have so many unused combinations that the remaining space would be incomprehensible. This isn't just we won't run out in practice. This is a mathematical statement. The number of unique QR codes is so astronomically large that it transcends any physical interpretation. The future of QR codes. So given that QR codes are essentially inexhaustible, what does the future look like? 1. Digital product passports. The European Union is already implementing regulations requiring physical products to carry digital product passports, persistent scannable identifiers that track a product's full life cycle, where it was made, what it's made of, how to recycle it. QR codes are the leading candidate. Imagine every piece of clothing, every appliance, every piece of furniture having a code that carries its entire history. 2. Healthcare and medicine. QR codes on medication bottles can link to real-time dosing instructions, drug interaction checkers, and even patient-specific information. In clinical settings, every vial, every sample, every patient wristband could carry a unique, scannable ID3. Smart cities infrastructure with embedded QR codes. Bridges that tell inspectors their maintenance history, roads that tell your car about upcoming hazards, trees in public parks that tell you their species and age. 4. Authentication and anti-counterfeiting. High-security QR codes, encrypted and cryptographically signed, make counterfeiting products dramatically harder. Luxury brands and pharmaceutical companies are already using this. 5. Invisible QR codes. Researchers are developing QR codes printed with UV-reactive or infrared ink, invisible to the naked eye but readable by the right scanner. A world of hidden information embedded in everything around us. The QR code was designed in 1994 to track car parts. 30 years later, it is woven into the global economy, healthcare systems, payments infrastructure, and identity verification, and it still has essentially infinite room to grow. Why this matters, the bigger picture. Here's what I find genuinely profound about all of this. We live in an era obsessed with scarcity, limited resources, finite time, not enough of everything. But information doesn't work like that. The space of possible QR codes is a perfect illustration of something that mathematicians and information theorists have known for a long time. The universe of possible information is essentially boundless, even from very simple building blocks. 2 states: black, white, on, off, 0, 1. Arrange enough of them in enough combinations, and you get a space so vast it exceeds the physical universe. Claude Shannon, the father of information theory, figured this out in 1948. He showed that information could be quantified, compressed, and transmitted with mathematical precision. What he understood, and what QR codes demonstrate so elegantly, is that digital information scales in a way physical matter never can. A warehouse full of filing cabinets runs out of space. A library runs out of shelves. A phone runs out of memory. But the abstract space of possible information, it doesn't run out. It just keeps going. Every time you scan a QR code, you're participating in one of the most elegant systems humans have ever built. A tiny grid of squares that encodes information redundantly, reads reliably in milliseconds, scales infinitely, and costs essentially nothing to generate. Not bad for something invented to track car parts. So, to answer the question, will we ever run out of QR codes? No. Mathematically, provably, cosmically, no. The number of possible unique QR codes is larger than the number of atoms in the observable universe. Even if every person on Earth generated 1 billion QR codes every second for the entire age of the universe, we wouldn't make a dent. And honestly, I think that's kind of beautiful. In a world of finite resources and real constraints, there are still some things that are, for all practical purposes, inexhaustible. And one of them is this unassuming little black and white square.